Okay, thank you very much for giving me this opportunity, this special opportunity. I'm humbled by it. And for the AAS Kamide Lecture 2022, the title of my talk is Synchronicity Discovered in the Gulf Stream and Kuroshio, A Path to Understanding Mid-Latitude Extreme Weather. I'm Tsubasa Kohyama, an assistant professor at the Department of Information Sciences, Ocha no Mizu University in Tokyo. First, the content of this talk was already published in Science on 15 October 2021. And my co-authors are Dr. Yamagami, Miura, Kido, Tatebe, and Watanabe. So if you're interested in this talk, please go to this particular publication. Okay, so let's go to the introduction. The western boundary currents are known as the strong warm currents on the on the west side of the ocean basin, the ocean basin. So the examples are like Gulf Stream east to the American continent, and the Kuroshio which is on the east of the Eurasian continent. But there are also similar warm currents in the southern hemisphere as well. And so question is why are Kuroshio and Gulf Stream so important? There are several reasons. The first reason is that they are the strongest currents in the northern hemisphere. And therefore, it maintains the energy balance in the climate system by transporting heat forward. And a little bit of societal reasons are like they are releasing heat toward the atmosphere along the coast of large metropolitan area, and therefore they influences on the extreme weather and fisheries production. So the motivation of this study is that Gulf Stream and Kuroshio were extremely warm in 2018. So here I'm showing the sea surface temperature anomalies from January through June of 2018. And we found that in both Kuroshio and Gulf Stream regions, there are many points where the sea surface temperature were warmer than 2 standard deviations. So we just wondered if it could be just a chance coincidence. Therefore, our scientific question is, could Gulf Stream and Kuroshio be possibly synchronized? So here, first we define 2 boxes. One is a Kuroshio box, and the other is a Gulf Stream box. And it is indicated in this map. And so we are now showing the time series, actually standardized time series of Gulf Stream sea surface temperature anomalies and Kuroshio sea surface temperature anomalies. And as you can see, these 2 time series are very well coherent. And the black curve is the BCS index, which we'll define later. So anyways, from this figure, we could say that there must be a fundamental physical explanation to explain this synchronicity. And we have referred to this synchronicity as the boundary current synchronization, or BCS. And interestingly, some high-resolution climate models reproduce beautiful BCS. So here, again, I'm showing the low-pass filter time series and the BCS index. Okay, so in the upper time series is the observations during the satellite era. And this is basically identical to what I showed in the previous slide. But also GFDL CM4C 192, which is a GFDL model with high resolution atmosphere, also exhibits this synchronicity very well. So one interesting thing of this BCS phenomenon, I think, is that it is only reproduced by some high-resolution climate models. And so I will also further demonstrate this synchronicity that Gulf Stream and Kuroshio SSD are coherent for the decadal timescale only. So here I'm showing the coherence spectra. Okay. So the black curve is observations, and which surpasses the confidence, 95% confidence level only at the longer time scale, very low frequency band. And red solid curve is the GFDLCF 192, and the blue solid curve is MIROC 6 sub-HIRES, which is also a high-resolution version of a Japanese climate model. Okay, and the other two models, which is GFDLCM4 and MIROC 6, are the counterparts with low resolution. Okay, so from here we can say that models with higher resolutions reproduce BCS better. And we have also calculated the lag correlations, and lag correlations again are almost zero lag. And again, models with higher resolutions do a better job reproducing BCS. Okay, so now the question is, why is high resolution important? So here I'm showing the animation of both low resolution MIROC 6 and the high resolution version MIROC 6 sub-HIRES, which has a finer ocean, right? And as you can see, the MIROC 6 sub-HIRES permits oceanic eddies, and therefore the reproducibility of sea surface temperature fronts appears to be important. Okay, so like this, in the only high resolution models, as you can see, the Kuroshio meandering of, or like the SST fronts can be well reproduced. And so we think that this kind of fine structure is essential for the BCS. And so to investigate the synchronization further, we define the BCS index. So BCS index is basically the mean of two standardized sea surface temperature anomalies of Kuroshio and Gulf Stream regions. Okay, and the Gulf Stream region is defined as 35 north to 45 north and 70 west to 50 west. And Kuroshio sea surface temperature is 35 north to 45 north and 115 east and 170 east, which are carefully chosen to exploit, I would say, the interannual variance. Okay. Actually, we have also more objectively defined this BCS index. Okay. So the sea surface temperature variability in this region is actually directly tied to the boundary currents. So here I'm showing the SVD performed over broader regions, which extracts almost identical covariability to the BCS index, BCS variability, which supports the notion that the objectivity of our definition of BCS index is valid. Okay, so both in GFDLC and 4C192 and MIROC 6 sub-HIRES, we can clearly see that the western boundary currents variability is essential for the sea surface temperature covariability of these two regions. And also this covariability is valid enough in the sense that it explains like 0.6 or 0.5 correlation coefficient of each region. Okay, and therefore the BCS index is almost identical to this more objective way of definition. And models with lower resolutions does not resolve the boundary current variability. So we basically did the same thing for lower resolutions, but of course, because the lower resolution models do not reproduce the meanderings of western boundary currents or anything else, like something like that, which means that the low resolution models do not exhibit large covariance between the two currents, which is not the case for observations. Okay, so it seems that again, the SST fronts or other kind of fine structure of western boundary current seems to be important for this particular global scale phenomenon. Okay, so we have also done the compositing analysis for both positive BCS index and the negative BCS index. So for the positive BCS, the boundary currents rip at the north, which means that warm sea surface temperature fronts, okay, as you can see. So here I'm showing the geostrophic current strength, which is a gradient of sea level, the absolute value of the gradient of sea level anomalies, and for MIROC 6 sub-HIRES. So when the when the BCS is positive, which means when both Kuroshio and Gulf Stream regions boxes are warmer, the Kuroshio is going all the way to the north. Kuroshio and Gulf Stream goes all the way to the north. But on the other hand, during the negative VCS, it stays in the south. Okay, so this dynamical process is a possible reason why low resolution models do not reproduce VCS. Okay, sorry, I have also prepared for this arrow. So in the positive VCS, it rips at Iwate or 40 degrees north, but in the negative events, it rips at Aogashima, 32 degrees north. But on the other hand, the Gulf Stream also rips at Virginia for 38 degrees north in the positive event, whereas it rips at South Carolina 32 degrees north in the negative VCS event. And so which is consistent with the dynamical processes as well. Okay, so now let's look at the atmosphere. And so VCS is associated with meridional migrations of the atmospheric jet stream. So here again, I'm showing both observed sea surface temperature and lower tropospheric zonal wind regressed onto the VCS index. Okay, and so we can see that when the boundary currents are warm, the jet stream migrates northward, which makes sense for the because the warm boundary currents can how can I say release the latent heat, which increases the barochronicity of the atmosphere, and it increases the associated jet stream. Okay, and this process seems to be reproduced in also the Myrock 6 sub-Hira's in the sense that in the both boundary currents are warm, the jet stream migrates northward. So from these evidences, we have come up with a hypothetical mechanism of BCS. Of course, we are not sure whether this hypothetical mechanism of BCS is correct, but at least it is good to speculate something. Okay, so here, if the western boundary currents are warmer for both regions, and the thermodynamics in thermodynamical sense, and it advex warm water, okay, and goes the SST variation, and it uses the SST variations, and this latent and sensible heating will then in turn migrates the jet stream, which then feeds back to the western boundary currents via wind stress and weather. Okay, and therefore both Kuroshio and Gulf streams are tied through the atmospheric jet stream by exchanging the information of each phase of both Kuroshio and Gulf stream. And this idea is actually not the first, not original from our analysis, but it is rather, how can I say, it is rather proposed by Gallego and Sessi in 2001. So here I'm showing the schematic picture of the idealized model constructed by Gallego and Sessi 2001, in which two ocean basins, Pacific Ocean and Atlantic Ocean, are connected through the zonal mean atmosphere. So here on the right, I'm showing the modeled and observed time series of boundary currents and winds. So here we can see that the GC01 model is a Gallego and Sessi model is reproducing the BCS in a very good way compared to the observations shown at the bottom. So here again, I'm showing the observational time series, which seems at least consistent with the Gallego and Sessi model. So an idealized models are consistent with the notion that BCS could be an interbasin air-sea coupled mode. Okay, but still we have to discuss whether it is really a coupled mode. And our conclusion so far is that at least jet stream moves northward in both idealized and the AGCM simulations, atmospheric GCM simulations. So here I'm showing the correlations between the BCS index and lower tropospheric zonal wind at each latitude for both models and Gallego and Sessi model and observations. And we can see that the jet stream is going toward north. And also at the bottom, I'm showing the regression map of lower tropospheric zonal wind on the BCS calculated from the answerable mean of the MIROX sub-Hires AGCM runs. And again, we can see that there is a significant wind anomalies in the that exhibits the jet stream northward migration. Therefore, I would say that it is at least consistent with coupling, though it remains an open question. And our hypothesis is consistent with many previous studies like Ogawa et al. 2012 or Omrani et al. 2018. For example, Ogawa et al. 2012 already showed the dependence of the latitude of the tropospheric vestiges on an idealized extratropical sea surface front. So here, Ogawa et al. Used the idealized sea surface temperature front, which is shown as the sea surface temperature and its gradient. And so basically, they moved the SST gradient kind of artificially in the meridional direction. And they found that the jet latitude is like migrating as shown in the right panel. So here I'm showing the winter relationship between the latitude of the sea surface temperature front and latitude of the jet stream. And again, Ogawa et al. Showed that the sea surface, idealized sea surface temperature front can modulate the latitudinal position of the jet stream. So with realistic sea surface temperature fronts, the global scale mid-latitude LC coupled mode could be plausible. That's what we are now thinking about. Okay, and finally, I will quickly introduce the immediate implication for the extreme weather. So in the top panel, I'm showing the 2-meter air temperature in July regressed on the BCS index, which is very similar to what it was actually observed in July of 1994 or 2018, as you can see in the middle panel and the lower panel. So the regression map of air temperature on BCS looks similar to the temperature pattern in 1994 and 2018. And also to make it a little bit more convincing, we have also calculated the projected time series, which also supports this implication for extreme weather. So at the top, I'm showing the BCS index, and in the middle, I'm showing the projected time series of 2-meter air temperature in July onto the BCS pattern, which means that when this blue curve is positive, it means it's similar to BCS, and when it is negative, it is similar to the negative BCS. And on the right, on the red curve is also showing the similarity of 2-meter air temperature to 1994, 2018 July. So basically, I projected the 2-meter air temperature data onto the average of 1994 and 2018 pattern of July, which means that when this red index is positive, it is similar to 1994 or 2018 July. And the opposite is 1994, 2018 July. So again, because these 3 time series are similar, we could say that air temperature patterns similar to the one associated with BCS have been repeatedly observed, including in July of 1994 and 2018. So even though it is still an open question why, especially the July temperature pattern could be similar to what BCS suggests, but I think this is also an interesting implication. Okay, so let's go to the take-home points now. Conclusion 1 is that Gulf Stream and Kuroshio sea surface temperature are synchronized for the decadal timescale. And conclusion 2 is that some high-resolution models reproduce the synchronization well due to realistic sea surface temperature fronts. And conclusion 3 is that this synchronization may have implications for understanding mid-latitude extreme weather. Okay, so here are the three take-home points. So if you're interested, please go to our publication. Okay, so finally, I would like to state an acknowledgement. First, I would like to thank AS, Atmospheric Sciences Section President, and those who nominated me. Okay, thank you very much for this great opportunity. And my co-authors of this BCS paper, Dr. Yamagami, Dr. Kido, and Dr. Miura, and Dr. Tatebe, and Dr. Watanabe. And I especially thank my former postdoc supervisor, Dr. Hiroaki Miura, who gave me an opportunity to work on this this interesting, stimulating scientific question. Okay, and I would also like to thank my colleagues in Japan and in Seattle, where I spent graduate study. Where I did this graduate study, and I would especially like to thank my PhD advisor, Dr. Dennis Hartman, at the University of Washington. Okay, and also I would like to thank my students in Ocha no Mizu University. I have currently 13 students, and also there are some former students as well. And I would also like to thank friends. And finally, I would like to thank my family members, especially my wife, Rika Kohyama. Okay, so here's the end of my talk. Thank you so much. And I would like to take live questions.